Welcome to this video presentation, Why Should I Do FPGA Verification with VHDL? My name is David Clift and I'm an applications specialist for FirstEDA. FirstEDA is a value-added distributor of electronic design automation solutions in Northern Europe, specializing in software and hardware solutions for electronics design and verification. I'm joined today by Jim Lewis, founder of Synthworks. Jim has 28 years of design, teaching and problem-solving experience. In addition to working as the principal trainer for Synthworks, Jim also does ASIC and FPGA design, custom model development and consulting. He is also the founding member of the open source VHDL verification methodology, better known as OSVVM, and the principal architect of its packages and methodology. On top of this, Jim is also chair of the VHDL standardization group of the IEEE. Welcome, Jim. You sound really busy, so I'm glad that you can join us today. How are you?
Hi, David. Doing pretty good.
Yeah, that's good to hear. So, Jim, one of the trends in today's FPGAs seems to be the devices are growing ever bigger. And the engineers I'm talking to today are finding verification of these devices ever more complex. And a recent NMI survey showed that the biggest challenges engineers face today is RTL verification. Jim, with your long history in ASIC and FPGA design and verification, what has been your experience of verification of FPGAs? Is it best to do it in the lab, or is RTL verification of designs a better way to go with these large devices?
Well, David, it was never in my experience. It was never a question. I started as an ASIC designer, and with ASIC design, simply the cost of correcting mistakes after ASIC fabrication are just too high. So there, you had to do the simulation in the simulator up front. Now, on the other hand, as we get to FPGA, the question does get a little more interesting. So in my experience, though, we were making the, at the time, Actel, now Microsemi FPGAs, and they were, even at the time, they were $500 US to program an FPGA, so it was expensive. So still, we had to simulate. Going further, when we look at reprogrammable FPGAs, lab debug really only gives us access to external I/O and pre-selected internals. Okay, so for small designs, yeah, sure, you can get away with lab debug. But as soon as the FPGA gets large enough, lab debug can be challenging. In fact, I kind of have an analogy here for you. Lab debug is like randomly placing excess furniture in a room, turning out the lights, and expecting to find a specific item there. You can do it, certainly. It's just hard to do.
Yeah. That's a good analogy, Jim. Yeah, I can see where you're going with that. That's you're basically got a black box and you're sticking your hand in, not knowing what you're going to grab, trying to pull something out. So it's a challenging task, trying to get at the hidden innards from the outside when you may be I/O limited on the FPGA, especially.
So I do see, though, simulation and lab debug as a winning solution. Debugging in a simulator is fast, so we want to get basic functionality running in a simulator. My preference is to do the whole chip simulation in the simulator and then take everything to lab, because in the lab running tests is fast and we can find those things that we simply couldn't run long enough in our simulators.
Yeah, and yeah, that is certainly something I've come across working with engineers here in the UK. Is there are certain things you can't test in the simulator. If you've got a processor and you need to run it through an initialization sequence, or a recent example I saw was an FFT chain, and they needed to run several frames of data through it to make sure it was working. And to do that in the simulator, that to get sort of 10 milliseconds of real wall clock runtime in a simulator, they were spending several days to test that running in a simulation
Yeah.
environment. What was worse for that particular customer was they had to repeat the exercise at the gate level, and that took over a month to do. So there are certain things that are definitely better in the lab, but proving that the design works, I see as something we should be doing in the simulator today.
Yeah. Yeah. And you mentioned gate sims there. What I like doing with gate sims is start them running when I take the FPGA into the lab. And that way, if I find something interesting in the lab, the gate sims might take several days to run, but at least they're running concurrently with me doing things in the lab. I kind of like to think of my laptop or my computer as my minion, and I like my minions to be busy while I'm doing something else.
Very good philosophy there, Jim. So there are a number of techniques we can use in RTL verification. A lot of talk about constrained random and functional coverage analysis. Um, is that something I can easily do in VHDL?
Oh, absolutely. Um, in the OSVVM library, which I'm chief architect of, um, we support constrained random, we support functional coverage, and just like any other verification, it's a library that we're building on top of VHDL, and it's quite effective and it's quite concise.
I see. And I can mix those techniques with the current directed tests that I'm using today.
Oh, absolutely. Yeah, we tend to layer everything on top of each other, layer everything on top of a transaction test bench.
One of the biggest challenges facing FPGA designers and verification engineers today is how do they complete the verification of the design. In this presentation, we'll start to look at some of the simpler techniques for FPGA verification. So Jim, if I've never done any RTL verification before, where should I start?
Well, that's two questions in one. Where should I start and where do people start?
Oh, I'm sorry about
So if
that,
we
Jim.
look at where people typically start at, the basic first test bench just wraps around your design. And then they simply drive signals to the design under test. Basically, the goal here or what's being done here is you replicate the lab environment and you drive your signals directly. Okay, so we need to put some waveforms on the CPU interface. We directly put those waveforms on the interface. And then our test in this scenario consists of tens, hundreds, thousands of these replicated code sequences. Okay, this is not a great place to start. It tends to be tedious, it tends to be time consuming, and it's very easy to make mistakes in any one of the individual sequences. And then on top of that, if the interface happens to change, there's a huge amount of code that needs to be modified. Every sequence needs to be edited, and it can be very painful. Beyond that, the code's not so readable. It's really hard to see what the test does. We tend to get lost in the coding details of the test.
Yeah, I can see that from the short example you've got there. Maintainability also I would think is not that brilliant.
So the next place where I recommend people start to explore or start to venture is using transactions. So a transaction is just a very fancy word for an interface operation. Okay, an interface operation such as a CPU read cycle, such as a CPU write cycle, or if you're working with a UART-like device, a UART send and a UART get. Okay, you look at basically what are the operations happening on the interface, and we're going to encapsulate those into subprograms. Okay, so in this scenario then, we have subprogram calls that create the tests. Okay, and a test consists of tens, hundreds, thousands of these, but now we can see from a higher level, okay, what's happening in a test. So the benefit here is it simplifies and accelerates writing tests. The test maintenance is easy. The interface changes, we edit the procedure that's behind this, change the code in one spot, test it, make sure that it works, and then every other call to it works correctly. Beyond that, it's readable. We can explain to members of our community, including the software and system engineering team, what these procedures do, and they can see what the test does, and perhaps recommend additional tests. And then beyond that, transactions become the base layer for all other testing.
Thank you, Jim. That's very interesting and informative. And I can see the definite advantage of doing that. The understandability of the code is increased quite considerably compared to the original brute force methodology that you were using. Well, thank you for joining us today, Jim. It's been a pleasure having you, as always.
Thanks, David.
Thank you for joining us in this discussion. Watch out for our next video when we'll be looking at verification techniques using bus functional models. If you require further information, please visit our website at www.firsteda.com.